Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Science and Technology, Hyderabad, India. So today the topic is equivalent circuits and switching times of the PN junction diode. Let us get into overview of these topics. We are going to study equivalent circuits of the PN junction diode and piecewise linear model of the PN junction diode, and then what is the switching times of the diode, how the diode can be used as a switch, and conclude with the summary. If you see the equivalent circuit of a diode means what? So far we have discussed the diode as an individual element, its characteristics, how the PN junction diode behaves when it is connected in forward bias and reverse bias. And now if you add or integrate this diode in a circuit, then what happens to the diode behavior? Now let us see what is the current flowing through that particular circuit when is integrated with a diode. So here we have a circuit which is a diode equivalent circuit. So we have a current limiting resistor, and the voltage across this resistor is represented with VR, and Vs is the source voltage and V is the voltage across the diode to be measured. So here if you apply KVL to this loop or circuit in this electrical circuit, then what happens? What is the voltage, source voltage here? It is given by I into R, that is this one, I into R plus the voltage across the diode. So this IR is also voltage drop in the circuit, and the total source voltage is approximately equal to the combination of this IR and I into R and the diode voltage. And how to get the current from this is I is equal to Vs by R. So we know the Ohm's law, V is equal to IR, so R is equal to V by I. So here I is the total current through this circuit which is integrated with the diode is I is equal to Vs by R minus V by R. And similarly we know that the diode current flowing through the diode current is given by I is equal to I naught into e power V by eta Vt minus 1, and Vs is equal to I naught into R into e power V by eta Vt minus 1 plus V. So if you substitute here in place of this, we can write like this. So we have substituted in this, so therefore Vs becomes like this. Okay, so in this way you can able to derive a expression for source voltage in a equivalent diode equivalent circuit. Now let us see how this diode behaves when it is connected in a circuit. So first let us see what is the DC load analysis and quiescent point. So what is quiescent point? Quiescent point is also called as operating point. This is also called as operating point. So see here, so this is the VI characteristics of a normal PN junction diode. So on x-axis we will take V, and on y-axis we will take I. So this is the expression VI characteristics of a PN junction diode. Okay, so this voltage is nothing but cut-in voltage, we know. And what is this? This is nothing but the symbol represented by plus here, which is Vs, that means source voltage. And in the second figure you can observe linear, so that is the which is the linear graph we have. Okay, this is the resistance IR, and this is the expression, this is the circuit VI characteristics of the across the resistor. So this is VR and this is IR. So voltage across the resistor and voltage across the current across the resistor. So if you, which implies, see here, so we have added Vs, added to Vs. So what happens here? So we have pushed this circuit in the opposite side, that is 1 by, slope will becomes minus 1 by R. Here slope will be R, so here slope will be minus 1 by R. That is flipped resistor line. Okay, and this point is nothing but operating point. So operating point means which allows the current to flow for a specific applied voltage, input voltage. Okay, and here also you can see, observe here. So if you combine these two, what happens? You will get the operating point, quiescent point of the particular diode. So see here, you can also observe here the diode characteristics operating point. So this is the DC load line, So which is represents the operating point or the minimum voltage required for a diode to conduct. Okay, and now, so all these stuff have we had from Salivahana, and now let us see the what is the difference between ideal and practical diode. So here this is the ideal diode, anode and cathode, and here anode and cathode. Okay, so ideal diode usually, so large current will flow ideally. So large current means less resistance of almost zero resistance, because in ideal diode there is no restriction. So large amount of current flowing to the diode and zero resistance. So whereas coming to the practical, so there is some resistance we have to consider, and that too forward resistance of the diode we have to consider. And then this is the cut-in voltage, battery voltage, you can say cut-in voltage or V gamma. So if you consider practically, we have to consider all these resistances and cut-in voltages, so that your equivalent diode practical circuit will be shown like this. Okay, so in this there is some amount of resistance is there, so that the current is minimum current. So here in this ideal case, large current, amount of current will be flowing through the diode. In practical, less amount of current will be flowing there. So there is another important property of a diode is a linear model. So piecewise linear. So we know that what is linear. Linear means what? If you consider the graph between voltage and current. So if the voltage increasing, current also increasing. Voltage increasing, current also increasing. So this is the linear curve. Okay. So this is the ideal case of a diode. So current increases, voltage increases, current also increases. So in such case, we can say the characteristics is nothing but linear. But whereas in practical, the current is not ideal or not constant, and initially the moment you apply the input voltage, the current is not conducting. The current is not flowing to the diode initially. So at a particular voltage, that is cut-in voltage, the current rises like this suddenly. So this voltage is nothing but cut-in voltage or reference voltage or threshold voltage, like that. Okay. So now let us see different equivalent models, diode equivalent circuit models. Here we have circuit models depending upon the different resistances. After considering different resistors. So see, first one is piecewise linear model. So what do you mean by this piecewise linear model? Very, very important property of a diode, because see here we consider V gamma, the cut-in voltage is not zero, and here the forward resistance also not zero, but the reverse resistance is infinity. In such case, the characteristics will be like this. Piecewise linear. Piecewise means this one. So initially there is no current flow even we are applying voltage. Even we are applying input voltage, there is no current flow. Current is zero. But only at the particular voltage, that is cut-in voltage, the current rises abruptly. So that means the voltage increases, current also increases. Voltage increases from this point. Hence it is called a piecewise linear. And simplified model, if you consider, so here we consider only the cut-in voltage of the particular silicon or germanium semiconducting material, and we consider RF is equal to 0. So there is no forward resistance of the diode, and RR also infinity. So in such case, the diode will have characteristics like this. So we consider only V gamma, that is cut-in voltage. From this cut-in voltage, if you further increase, the diode current increases rapidly. If you consider the third model, that is ideal model, so here we consider there is no cut-in voltage. We don't consider cut-in voltage of the diode, the semiconducting diode. RF is equal to 0, forward resistance, and RR is equal to infinity. In such case, so it is shows the characteristic shows like a pulse, impulse response. So that means at a t is equal to 0, even though we are not applying any input voltage, the current rises rapidly. Okay. So these are the diode equivalent circuit models. Next, let us see the switching times of a diode. So what is the switching times of a diode means? So the diode can also operate as a switch. So if you connect it in a forward bias condition, it acts as a on switch. In contrast to this, if you apply reverse bias to a diode, it acts as a off switch. So switching times, we have to consider here forward recovery time for a diode voltage to reach from reverse to forward. So when a diode is already connected in reverse bias condition, so when you apply now forward bias, so it has to take some time. Okay. So that is called forward recovery time for the diode voltage to reach from the reverse bias to forward bias, Similarly, so to acquire some specific value, specific voltage. Similarly, reverse recovery time is to stop conducting current in forward bias. So forward to reverse bias. So it is when forward bias to reverse bias. So it is called a reverse recovery time. So when a diode change its state from equilibrium state of let us say equilibrium state, for example, if it is in forward bias for a specific time, then it is called steady state or equilibrium state. So whenever you change that state from forward bias to reverse bias, it suddenly changes its state, right? That means it cannot change its state immediately. It will take some time. So why? Because so if you observe this figure, see here the carrier concept. This is the junction, and this is p-type material and n-type material, and here this is the equilibrium condition. Equilibrium condition means where the carrier concentration is constant. So here NP naught means what? The carrier concentration of the electrons in p side. Here the Pn naught indicates what? The carrier concentration of the holes in n side at equilibrium condition. So therefore, see here at equilibrium condition there is a maximum carrier concentration is more, and when it away from the junction, the carrier concentration is more, and when it reaches towards the junction, the carrier concentration of the electrons will decreases to 0. So it gradually decreases like this. Similarly, on p side also, the carrier concentration of the holes in n side decreases while it reaches towards the junction. Okay. So that means there is some time required to settle down. So here if you see this second figure, so see here it is in the forward. Whenever you apply the forward bias junction, so initially the carrier concentration at the junction is more. So while it away from the junction, the carrier concentration, that is, see, whenever you apply the forward bias, let us say p-type n-type material, whenever you apply the forward bias condition, so what happens? So the positive holes are repelled by this positive terminal, so therefore they attracted towards they move towards the n-type material and crosses the junction. So in such case, the carrier concentration at the junction initially will be increases, and as it move away from the junction, the carrier concentration decreases. So that shows this figure. And similarly on n side also same. The carrier concentration, the minority charge carrier concentration, here we are concentrating on minority charge carrier concentration, because see here the holes are moved towards the n side. Entry into the n side means here the holes, the minority charge carriers on n side will increases. The minority charge carrier concentration increases at the junction, and it away from the junction, the carrier concentration of the minority charge carriers will be decreases like this. So this is the excess hole concentration. So here some excess hole concentration will be available at the n side. So this indicates the excess hole concentration, and here excess electron concentration on p side, and this indicates the excess hole concentration. So that means we are talking about the minority charge carrier concentration on p side on n side. So therefore this is the equilibrium condition. So this is the difference between the minority charge carrier concentration on n side and p side. So based on this we can analyze the switching time of the diode. See here, this is the figure represents the switching times of a PN junction diode. So here this is the input signal, a rectangular signal is applied to a diode. Okay, so we have a forward voltage and reverse voltage minus VF minus VR, and this is the time T1. So if you observe, this is B and this is C. This figure, this characteristic shows that the excess carrier concentration. What kind of concentration? Minority charge carrier concentration, Pn minus Pn naught at the junction at equilibrium. See here the carrier concentration decreases slowly like this. Okay. Similarly, the current, at the same time the current also we can draw. The current also given by IF is equal to VF by RL, and then so this is represented like this. Okay. At a T2, that means when it changes from forward bias to reverse bias, so it will take some time. So that indicates slowly. So this is the slowly increasing like this. Okay. So that is the time required by the charge carriers to settle down, and this gap is nothing but reverse saturation current. So these are the the reverse saturation current is due to minority charge carriers, we know, and this is the last one is given by this, the voltage, output voltage after changing the state of a diode from forward bias to reverse bias or reverse bias to forward bias. So here this is the positive, and the voltage will be forward bias voltage shows, and then TT. So transition time is this one, and we have a storage time also. So storage time means what? So the time required by the diode voltage to change from its state from forward to reverse and then reverse to forward. So that shows the minority carrier storage. It's given by storage time. And similarly, transition time. Transition time is completely changes its state from one state to another state. The time required by the diode to change its states from completely change its state from, or transition. Transition means change completely from forward to reverse bias. So this is the switching times of a diode. And now this concludes your chapter 1, that is diode introduction. So today the summary is we have discussed the equivalent circuits of a diode, load analysis, load line analysis, DC load line analysis, ideal versus practical diodes we have discussed, equivalent circuits, and switching times of the diode. Okay, so next topic will be unit 2, that is diode applications. Diode applications are nothing but rectifiers, filters, and so on. Okay, thank you.